Welcome to ECE 442. I hope I didn't scare you too much with this face right now, but I thought I would just let you know that everything is okay here for now. And what I wanted to do in this short video for the 442-542 students is actually work through a summary of what we talked about yesterday in office hours. If you were unable to join us during the virtual office hours on Zoom yesterday, I'm hoping that this particular summary will provide enough information to get you through homework problem set number 4. The questions that were raised were actually, I've consolidated those here. If I can get my mouse to work, for some reason it's not. Now it is, and it's scaling everything. So hopefully you know that you have to be somewhat flexible with me now in this new environment of trying to entertain you, I guess, with all this technology that we have available to us. What we had yesterday was the first question concerned homework problem number 1B on homework set number 4, and I would just refer you to page 8 in lecture 4.1, but it really focused on how do you work with the z-transform of a transform expression that involves more than just one denominator factor. Here we have really 3 factors in the denominator, and I want to quickly talk about that. How do we compute phi? I'm really wanting you to do that. This is, I think, homework problem number, what is it? I think homework problem number 2 on homework assignment 4. Look at 4.3, lecture 4.3b on page 4, how to do that by hand. And we'll go through that a little bit more carefully after I run through these questions. If you have no need for any of these answers to these questions, then you can simply turn off the video. In computing gamma in the same problem, I guess really you don't need to evaluate the integral. That's a little bit tedious. So in this case, if you can set it up, that should be sufficient. The fourth question concerned problem number 2, and what is this scaling factor of 160? In a nutshell, replace the u of t that was found in lecture 4.3b with a new expression, 160 u of t. So the 160 incorporates the scaling factor. Another question concerned what's this reasonable sample period, and that's asked in a couple of different places at least in homework set number 4, problems 1a and 2b. And it really boils down to this rule of thumb that we've established in this class is depending on what frequency is the highest in your system, that's what I'm labeling omega sub h here, you want to sample 30 times that. And that frequency, omega sub s, is related to the sample period inversely through this 2 pi factor, or omega sub s is 2 pi over t. If you set that equal to 30 omega sub h, what does t look like? Is it reasonable? That's what I'm really after in homework number 4, in homework number 4. And the last question concerned the trapezoidal discrete equivalent in MATLAB, and actually MATLAB, this C to D function inside MATLAB, you can allow it or make it perform many different kinds of zero-order hold operations depending on the method you insert in the third argument of the C to D function. The first argument is the system, the middle argument is the sample period, and the third argument is the method. And if you want the trapezoidal method, then in MATLAB they're really referring to that as the Tustin method. So you would put in single quotes TUSTIN if you wanted to use or find the discrete equivalent using the trapezoidal strategy, or you might hear that referred to as the bilinear strategy. And if this is too quick, just do a help C to D inside MATLAB, and that should help you. If you do not even include that third argument, the default will be to give you a zero order hold. And remember, we have two different scenarios of discrete equivalence. The first scenario is where you're just really doing a direct translation from a filter or a controller and trying to find a D of Z from a D of S. The second scenario or second strategy is in MATLAB the default strategy, which is the zero order hold equivalent, and that's the strategy where we actually incorporate the dynamic behavior of the zero order hold together with the plant itself, and that we will talk about now actually in question number 1 during the office hour period. The zero order hold equivalent is this expression that we derived in lecture 4.1. And you need that factor 1 minus z to the minus 1 to scale the z transform of g of s over s. And you actually then need to find what's going on inside these curly braces relative to g of s over s. In problem number 1, g of s is given as 1 over s times s plus 1. That means then that g of s over s is actually 1 over s squared times the quantity s plus 1. And where maybe I wasn't very clear during the lecture, you can't just pull out factors relative to this z transform operation. Remember, we were using this sort of shorthand notation, and what's going on is really we are inverse Laplace transforming everything inside the curly braces. We are then sampling it, and then that sampled sequence is what we are z transforming. And that's not the same as saying, oh, let me just partition that or factor that. You can't do that. You can't say that the z transform of 1 over s squared times s plus 1 is equal to the z transform of 1 over s squared times the z transform of 1 over s plus 1. You have to consider that entire product expression as one unit or one quantity. And if you do it by hand, what I mean by that, to do it by hand, is I'm really wanting you to look in the table and find the entry in the table or entries in the table that correspond to 1 over s squared s plus 1. And the table that I'm referring to can be found in the exam 2 material module on D2L, and you're really trying to find, oh, inside the curly braces, do I have something that looks like that? Or do I have something that looks like that? Or do I have a linear combination of those? Let's now look at what we could do. One approach would be to partial fraction expand what's inside the curly braces. And that then goes back to your earlier courses, and it now says, oh, I have a repeated factor at the origin, that's this s squared. I actually need then an a over s plus a b over s squared plus a c over s plus 1. And now what you can do is you can go to your table and try to find this term, then find that term, and then find that term. This is granted after you've found A, B, and C by means of a partial fraction expansion. And depending on what kind of calculator you possess or have access to, you can use the expand function on a TI Inspire, and it will do this for you in one key return. But in this case, if we now have A over S, and if we have B over S squared, and we have C over S plus 1, you can actually go to this z transform table and say, oh, the first one, this would now be scaled by a, whatever that a ends up being. A times 1 over s, oh, that just means that I can now have an a times 1 over 1 minus z to the minus 1. When I pull that out of, or when I perform this operation, when I take the z transform of a over s, now you can replace that with this a over 1 minus z to the minus 1. That's why I'm saying, oh, that's just row number 3. This b over s squared, now you're simply going down the rows and you're saying, do I see that? Oh, I see it. And here, if I just scaled that by b over s squared, now if I scale this by b, I can now replace all of this with what I have in the last column of this z transform table, or this Laplace transform z transform table. Finally then, if we look at the third term, that's c over s plus 1, you go over here and you say, do I see a 1 over s plus something? And here, if you just let little a equal to 1 and scale that by c, you now see that you see SEE, that you can now replace all of this with the c over 1 minus e to the minus at z to the minus 1. Remember, you can't forget the 1 minus z to the minus 1 factor when you're doing the zero order hold equivalent. You put that in place, but now you see that all of this, if you do it this first approach, you now have 3 different terms which will now be scaled by each of those terms, scaled by 1 minus z to the minus 1. Another approach, or another method, would be to, wait a minute, I can actually find, if I go far enough down, look at this. Now if I let little a equal 1, wow, they've already worked out, obviously it looks a little bit messy, but you know little a, hopefully you have determined or are given capital T. Now you have the z transform in one step of this bracketed expression, and then you would just multiply it by z to the minus 1, and this is now going to be what you put into that square bracket there. Hopefully that now clarifies a little bit from or beyond what we talked about in lecture 4.1, when maybe I was simply doing very simple expressions in terms this associated with the z transform of curly brace operation. When this becomes an expression that contains more than one factor in the denominator, then you need to partial fraction expand that or find something in the table that allows you to find its representation. So if you now had a over s times the quantity s plus a inside the curly braces, now you have a row for that, and you could immediately write down that expression for the z transform. Question 2. When you're doing this by hand, the most direct or straightforward way to find this matrix exponential, e to the matrix a, t as a scalar, that's our sample period, is to really find the inverse Laplace transform of a matrix. The matrix now is an expression in terms of the complex variable s. Now you just have a lot of Laplace transformed quantities in this matrix, which you've now inverted. You solve that for the inverse Laplace transform and evaluate that wherever you have a little t, you replace it with the sample period capital T, and that would give you the e to the a t expression, which gives you phi. Right, let's say the next step in that process is to find the input matrix in the discrete equivalent. That's this gamma. That's now the integral from 0 to the sample period of this matrix e to the a, now we're using a variable mu as our variable of integration, times the analog system. So this input matrix here is for the discrete time setting, and this input matrix is in your analog state space representation, or in the continuous time system. I'm going to go ahead and allow you to leave that in an unintegrated form. You can just set up the integral, but it would be helpful for you to combine. Let's say e to the a mu is a 2 by 2 matrix and b is a 2 by 1 matrix. You combine those. Now you just have to worry about a 2 by 1 vector, and you'll now have two integrals to perform to generate this gamma matrix. But we can do that numerically inside MATLAB, and that's what we will use in reality. Another question during office hours is, where does this scaling factor, or how do I put that into my problem? This is really all I'm wanting you to do, is replace the u of t with 160 u of t. I want you to scale that applied force that's going, or applying the force to this mass, where the mass is now interconnected to a permanent structure through a spring and a dashpot. The spring has a spring constant k, the dashpot has a dashpot value of b, and we now have the position and velocity of that mass. And if you worked through the free body diagram, and if you represent ma, or mass times acceleration, by this inertial force, you can now say, oh, the sum of all these forces equals 0, or the algebraic sum. You have the applied force going to the right. All of these other forces are actually opposing the movement to the right. You have your spring force, which is ky. You have your dashpot, or damping force, which is b times the velocity of y, or the velocity of that mass, which is y prime. And you have your inertial force, which is m y double prime, or m times the acceleration of that mass. All of that is equal to 160 u of t. And that should now allow you the information you need to slightly modify the block diagram that we were using in an earlier lecture, which was actually lecture 4.3b, in order to work that problem. The other question during office hours pertained to, when is the sample period t, or is this a reasonable sample period? Omega sub h is the highest frequency. Our rule of thumb is we want to sample, or we want our sampling frequency to equal 30 times the highest frequency in our system. Let's just look at an example. Suppose omega sub h is 5 radians per second. What is a reasonable sample period? Well, we know then from our rule of thumb, that's the 30 omega sub h, and if omega sub h, if our highest frequency in the system, let's say that's our closed loop bandwidth, that's 5, or let's say that we say, oh, we have a signal and the highest frequency in that signal is 5 radians per second, there's the 5. That's the omega sub h. In this case, we say, oh, our sampling frequency needs to be close to 150 radians per second. But we know that the sampling frequency is related to our sample period by omega sub s is equal to 2 pi over t. We just computed, based on the highest frequency, that omega sub s is 150. We can now solve that for the sample period, and we now have t is equal to 2 pi over 150. And we can do just the approximation of setting pi equal to 3, and that allows us now to say, oh, a reasonable sample period would be 40 milliseconds, or 0.04 seconds. That's really what was talked about during the office hours. Those office hours may be recorded, but I don't think I'm going to display those. I'll let you maybe see my face during these summaries, but if something I think important comes out of those office hours, I'll try to make it available like I'm doing here, and hopefully these won't scare you. Hopefully these will be helpful.